over the years in teaching this class is that my students are very good at identifying stereocenters. And so again, the main thing you're going to come away with from this class today is going to be identifying a stereocenter as being R or S, okay? There's a name for it. It's called the Kohn-Ingold-Prelog rules, okay? It's named after 3 different people, but students usually just refer to it as R and S, and that's totally fine with me. And we did a little bit of an introduction to stereoisomerism last class. So I'll just review quickly. We talked about different types of isomers. And if we go right back to the beginning of the class, or even your general chemistry 1 days, you would have learned about constitutional isomers. These are compounds that have the same molecular formula, but have a different connectivity of atoms. And the classic example that we use is C2H6O, which can be either ethanol, which has a boiling point of around 78 degrees Celsius, or dimethyl ether, which has a boiling point lower than 0 degrees Celsius. So it's a gas at room temperature. But then we said, okay, well, what's a stereoisomer? That's the topic of this channel, okay? So now we're talking about same molecular formula, same connectivity. Now, connectivity is just a fancy word to say the atoms are connected in the same order, but their arrangement in 3 dimensions or their arrangement in space differs, okay? And so we said a good example of that would be your left and right hands, right? They're connected in the same way. However, when you put them on top of each other, you see that they are non-superimposable. And I actually brought 2 molecules with me this morning that are mirror images of each other. And I brought this up last lecture. I said, if you have a carbon, so that's this black sphere in the middle, that's attached to 4 different groups, okay, not necessarily 4 different atoms, 4 different groups. So you see that each of these carbons in the center is attached to a green, a white, a red, and a black. Do you see how they're mirror images of each other? Okay. However, when I try to overlap them, you see that the green and the white don't overlap each other. And if you're thinking, oh, you're just holding it the wrong way. No, it doesn't matter. You can twist them any way you want, and you will never be able to overlap them. You'll see that 2 of the groups are going to overlap, but 2 of them will not overlap. And so we say these are non-superimposable mirror images. Again, we call them enantiomers, and human hands would be an example of that. But we said, besides non-superimposable mirror images, there are other types of stereoisomerism. And we brought up cis and trans with respect to a ring. And so if we have a ring, when we have cis substituents, they're on the same side of the ring, okay? Whereas if they're trans, they're on opposite sides of the ring. But if you look at these 2 compounds that are shown here, they're both isomers of 1,2-dimethyl cyclohexane. You with me on that, right? They're connected in the same order. You have a 6-membered ring, you have 1 methyl group, and then on the next door carbon, you have another methyl group. However, if you try to overlap this structure and this structure, you see that they are non-superimposable. You with me on that? So we would say they are what? Stereoisomers of each other. Now, if you want to get into more detail, if you've read the chapter already and you say, well, if they're not enantiomers, what are they? Okay, we're going to cover that in just a second, so don't stress about that. Then we said, well, not only can you have cis and trans on a ring, right? You can also have cis and trans with a double bond. And if you've never been introduced to this, I tried to introduce it last lecture, but you look at these 2 molecules. They're both isomers of 2-butene. We have a CH3 group, then we have a CH, we have a double bond, CH, then we have another CH3 group, right? Another methyl group. However, you see that the arrangements of the atoms in space are different. Again, give me a thumbs up if you see that, right? Remember, there's no rotation around a double bond. You can't do that, right? A double bond is rigid. There's no rotation there. And so we see that in the cis, the 2 hydrogens are on the same side, or you could say the 2 methyls are on the same side. And in the trans, you see the 2 hydrogens are on opposite sides of each other. So again, cis-trans isomerism in a ring or on a double bond, those are both different forms of stereoisomerism. Cool. So just kind of an introduction to the subject. So we mentioned this question last class, but we didn't do this question last class because we had just finished a quiz. But if we take a look at this compound, you see there's 3 double bonds in here. I have one highlighted in green, another yellow, another blue. Let's start with the one in green. Would you guys designate this as being cis, trans, or not stereoisomeric? It would be cis, right? Because you can clearly see that these 2 hydrogens are on the same side of the double bond, and so this one would be cis. Absolutely, okay? What about the one in blue? Anybody have a feeling about the one in blue? It's trans, right? Because I have a hydrogen going up, I have another one going down inside the ring like this, and so this one would be trans. The last one, the answer is neither. Okay, it's not cis and it's not trans. In order for a double bond to be cis or trans, it has to have two groups on the two carbons of the double bond that are identical. And you're like, yeah, but you have two groups that are identical here, right? You have two hydrogens. Well, whenever you have two groups that are identical on the same carbon of a double bond, it can't be a stereoisomer, right? If you were to call it cis, right, it's cis to what? You know, this one or this one, right? There's no differentiation between those two, and so the answer would be neither for this one. All right, good. So I think we can all identify cis trans and something that is neither cis nor trans. So then I brought up the word chirality, and I probably let it sneak out of my mouth this morning as well, but it's pronounced chirality, not chirality. So chirality and chiral molecules, and like I told you last lecture, there are many forms of stereoisomerism. We only look at a few in this class, and cis-trans isomerism is a type. Yes, it is totally a type of stereoisomerism, but there's other types of stereoisomeric relationships. And in order for us to define what those are, we have to start with chirality and define what a chiral molecule is. And so a chiral object is something that is asymmetric. And again, I know I keep going back to the same example, but all of us, I think, have the same examples on us, which is our two hands, okay? Again, they're mirror images of each other, so they have the same connectivity, but they are not identical, are they, right? They have a different arrangement in space. And so you can see this desk here would be another example of if you were to take the desk on the left and try to superimpose it on top of the desk on the right, since they're mirror images, right? The entrance, or whatever you call it, to the desk would be on opposite sides of each other. So we would say these are chiral objects. So you could even explain this to somebody in your everyday life, right? Somebody who doesn't study organic chemistry, you could explain to them the word chiral, what it means. You'd say, okay, if you have two objects, right, and you put them, you make a mirror, or if you have an object, you make its mirror image. If the mirror images are superimposable, you'd say it's not chiral. But if the mirror images are not superimposable, then you would say it's chiral, right? Does that make sense? Okay, so let's say you had like a picture of a balloon or something, and I'm being kind of silly here. Let's say you had a picture of a balloon. That's not a very good picture, but you can imagine if it was symmetrical, if I drew its mirror image, you would say it is not chiral, right? It's perfectly superimposable upon its mirror image. Again, maybe not the best example, but it'll do for now. Then I gave you a little blurb about why is this so important for us as organic chemistry students. I know not everybody, but some of us are interested in medicines. It's what I did for a long time. And so pharmacology, the way a molecule is going to interact inside a human body is going to be governed by chirality to some extent, because chirality exists in your receptors on the cells of your body, okay? And so when a pharmaceutical company designs a new drug, they usually design it as a chiral molecule. And there's a little blurb in the textbook about that. Marketing drugs as racemic mixtures or enantiopure. And I'll talk about that maybe later on if I have time. But again, I made these models this morning. You know, it's not very often I bring in a model kit, but I made these models on purpose to show you that you cannot overlap these two chiral molecules, right? They're mirror images of each other, but they're non-superimposable. And again, if you don't believe me, you can come and pick them up after class, or I can hand them out. I'll tell you what, you guys can pass them around and you can manipulate them anyway. Remember, you can't disconnect the bond, but you can try to overlap them, and you can prove to yourself that these are non-superimposable mirror images. And so what's the criteria that you and I are going to look for most of the time when we're trying to determine whether a molecule is chiral or not? So listen to me very carefully, is we are going to look for carbons, right? The element of the semester, right? Okay, we're going to look for carbons that are attached to 4 different groups. Okay, not necessarily 4 different atoms, but 4 different groups. And so if you take a look at this molecule here, okay, if we just look at that carbon that I highlighted in black there, you see it's attached to 4 different groups. It's not attached to 4 different atoms, is it? Because the ethyl and the methyl group are both connected by a carbon, but it's attached to 4 different groups, right? A hydroxyl, the OH, a proton, the hydrogen, a methyl group, and an ethyl group. Would you agree with me? Those are all different, right? They're all unique. And so we would say this is a chiral molecule. We draw its mirror image, and we see that they are non-superimposable. And so when an atom like carbon forms a tetrahedral center, right, and we're going to be dealing with sp3 hybridized carbons because the carbon has to be sp3 in order to be tetrahedral, with 4 different, remember, groups. If you want to write not atoms necessarily, but 4 different groups, attached to it. It's called a chiral center. Analyze the attachments for each chiral center below. Now it turns out that each one of these carbons that are highlighted in green, each one of these are chiral. Okay, but let's go over why they're chiral. If we take a look at this carbon, I'll highlight it in blue. Okay, would you agree that carbon is attached to 4 different groups? I see everybody nodding, right? We've got a chlorine. A chlorine is different than a hydrogen, certainly. Then we've got a methyl group here. And what kind of group is this guy here? What kind of group is that, everybody? It's an ethyl group, right? Methyl is not the same as ethyl, so certainly that's a chiral carbon. Now, if you look at the next one, I'll go a little bit faster. We have the proton, we have the hydrogen, we have a hydroxyl. Well, those are certainly different. Here, you guys just identified this a second ago as being an ethyl group. And then here we have a propyl group. Right? Ethyl and propyl are not identical. 4 different groups, right? And you're going to train your eye to recognize this very quickly. You will, and you're going to get good at it too. Take a look at the last one. Okay, we've got a bromine on the carbon. We've got a nice hydrogen atom here. Now, if you take a look at these 2 carbons, you can see these carbons are very different. I mean, if I just write here, this carbon, what's the hybridization of this carbon, everybody? It's sp3, right? This one is sp3, whereas this one is, I hear you guys whispering it, yeah, it's sp2. So obviously they're different carbons, and you can see they're attached to different things, right? One has a double bond, one has no double bond, so obviously they are non-identical. And again, you are going to train yourself. Like once you get some practice on looking at carbons and you say, oh, I'm trying to identify a chiral carbon, might you have to pore over it for a second? Like, ooh, is that chiral? Yes, no, I'm not sure. You know, it might take you a second, but that's normal. Okay, that's normal. So don't think, oh, I have to see everything immediately, right? We study it. We study it, okay? So let's see if we can study these compounds here. So we've got vitamin D, and we have ascorbic acid, which is vitamin C. Let's see if we can identify how many chiral centers in here. Now, I know this would take us a long time for me to just say, go for it, you guys. Like, try to identify them all. Let's start with vitamin C because there's less chiral centers in vitamin C. Let's just do it like this. We'll do it in kind of a quick way. If I highlight this carbon here, and remember, there's no trick questions in my class. Okay, I hate trick questions. Muhammad, is that a chiral carbon? No, why? What's the hybridization of that? It's sp2, okay? It's got nothing to do with chirality, right? This has nothing to do with chirality, right, Muhammad? This has nothing to do with chirality. Would you all agree with me on that? But let me throw this out to everybody, okay? Do you think, and again, I would never try to fool you, just think about it. Is this carbon, would this be a chiral or no? I see Chance and Heidi. No, that is not chiral. Why is it not chiral? Because it's attached to 2 hydrogens, right? Yeah, exactly. It's attached to 2 hydrogens. So you're saying it's attached to 2 hydrogens. Those are identical. So, and if you're thinking, well, hold on. That would mean any time you have a CH2, right, a methylene, the carbon can't be chiral. Every time I have one, and I'd say, absolutely. You're 100% correct on that assumption, yes. Okay, what if we try this one? I'll try a different color highlighter here. Let's try green. What about that carbon? Would that be chiral? What do you guys think? Yeah, I'd say it is, okay? So that carbon is attached to a hydrogen, which is not shown. It's also attached to this hydroxyl. Now, if I just delete this spinach here, what about this carbon that I'm putting in red and this carbon that I'm putting in blue? Are those 2 carbons identical to each other? Well, no, they're completely different. One's attached to a hydroxyl group, one's on a ring, you know, they're certainly not the same at all, okay? So that is definitely a stereocenter, right? Definitely a stereocenter. We'll try this one here. Again, there's no trick questions. Would this be a chiral center? I see everybody nodding, and you're all absolutely right on that assumption, right? And you're like, I don't even have to look that hard, Mr. Dion. I can tell I've got a hydrogen there. And then if I just look at the different carbons that it's attached to, look, I've got this carbon, I've got this carbon. Those 2 carbons certainly are identical, are they? The one in blue is sp3, the one in red is sp2. And you're like, this isn't even a carbon, it's an oxygen, okay? So these are certainly all different groups, so that carbon is certainly chiral, okay? So I'll tell you what we'll do is I'll give you guys some time, and today's Wednesday, we'll say Friday. We could kick the class off with this one on Friday and see if you can identify all the chiral centers in there, okay? just take a minute and see if you can fiddle around with it and find all the chiral centers, right? There's a lot of carbons in the molecule, so just give yourself some time to study those. All right, everybody give me a thumbs up if you're with me so far. Any questions so far? Anything burning? No? Okay, usually the first few parts aren't that bad. So some stereoisomers, you heard me say this word a bunch of times already, can also be classified as enantiomers. So enantiomers are going to come up a lot. And enantiomers are two molecules that are mirror images, but not superimposable, therefore not identical. We'll put here, i.e. hands, okay? So just like your hands, and I know I'll keep using the same example over and over and over, but it bears repeating. So again, you see these two molecules on the left that are enantiomers, and we call this sec-butyl alcohol. And then if you look at this trans compound here, so this is trans 1,2-dimethyl-cyclohexane. I mean, if I just take this molecule and I redraw it, okay, and just bear with me here. This is not going to be pretty, but it's for illustrative purposes only, okay? So if I take these here, this is terrible. Anyhow, if I put this hydrogen up here and this one, oh crap. Did I put my methyl group in the wrong place? I did, sugar. All right, I'll fix it. There we go. Again, I'm being a little bit ridiculous here, but if I was to take this molecule, which is the same as this one, and try to put it over top, right? Are you with me? See, this is why they pay me $3 an hour, right? And you can't overlap these on top of each other, but they are mirror images of one another, and therefore, we would classify them as enantiomers. So again, repeating the definition, and you guys are going to memorize the definition, and eventually it will become second nature. Two objects or two molecules for our class, okay, two molecules that are mirror images of each other, but they're non-superimposable, they're going to be enantiomers of each other. Cool? All right, there you go. And I'm going to give you some tricks for recognizing enantiomers in just a second that will make it way, very simple in certain cases. So, practice the skill. 5.8, what's this question about? For each of the following molecules, describe it as chiral or achiral and determine whether the molecule has an enantiomer or not. So I don't know if we're going to do all these because some of these are tricky. We might have to come back to them later. But let's just start with the first compound. Obviously, and maybe I shouldn't say obviously, but these are CH2s, right? So can a CH2 ever be chiral? No. Can a CH3 group ever be chiral? CH3, no, because it's attached to three things that are identical, okay? So whenever you see a CH2 group, a methylene, or a CH3, a methyl, and somebody asks you, is this carbon chiral? You say, no, of course not, okay? It's attached to two or three things that are identical, so it can't be. So there's one carbon left, and I know you guys have probably been, studying it while I'm rambling on here. But this carbon that I have highlighted in green, does anybody have a hunch about this one? Would that be chiral, yes or no? I see people saying no, right? And I think you're right. It's not chiral. So this would be an achiral compound, achiral. There's no chiral centers in there. And the reason why that carbon highlighted in green is not chiral is because it's attached to a hydroxyl, the OH. It's attached to a proton, but it's attached to two what? Ethyl groups, right? It's attached to two ethyl groups, okay? So the two ethyl groups are identical. Therefore, it's an achiral molecule. There's no chiral centers in it. Now, if we go to the one just to the right of it, the one with those two bromines, I see people shaking their heads already like, come on, Mr. Dion, don't waste our time, okay? Well, hold on. Let's just go over it quickly here. This carbon, obviously all the other carbons, right? This is a methyl group. That's not chiral. This is a methyl group. That's not chiral. This is a methylene, a CH2. That is not chiral. But that carbon that I have highlighted in green, why were you guys so adamant that this is not a chiral center? Because it's attached to two what? Two bromines, two groups that are identical. Absolutely. Absolutely. So we would say that this is an achiral molecule. So achiral. Okay, the next one, the one with the two hydroxyls on it that are next to each other, I'm going to come back to that one later because there's one other concept I want to review with you before we do that. However, if you look at the one in the bottom left-hand corner, would you describe those two bromines? So this is a 1,3, right? This is a 1, 2. This is 1,3-dibromocyclohexane. Would you guys describe this as cis or trans? And it's not a trick question. It would be trans, right? One bromine is pointing down and equatorial. The other one is up and axial. So down and up. So this is trans 1,2-dibromocyclohexane, or sorry, 1,3-dibromocyclohexane. And so if we draw the structure as a bond line structure, as a planar, instead of doing it as a chair, it actually makes it, and I will use the word, it makes it easier. So what we're going to do is this, is we're going to draw the mirror image. Okay, so we're going to imagine we have a mirror plane here, and we're going to draw what the reflection would look like. So the reflection would have this dash coming down here, and it would have this wedge like this. Are you with me on that? These are mirror images of each other. Does everybody see that I've just drawn the reflection the best I can? Now, are those superimposable on each other? Okay? Can I superimpose one upon the other? Does anybody know? The answer is no in this case. Right? If you take this one, and you try to plop it on top of here, well, obviously the dashes and wedges don't line up. And if you're saying, yeah, but Mr. Dion, you're not doing it right, all you need to do is flip this 180 degrees, and then they're going to overlap. No, they won't. No, they won't. Because this bromine that is pointing down, when you flip it, it's going to be pointing up. Right, Eric? Okay? So these two compounds would be enantiomers of each other. Right? They're non-superimposable mirror images. And so this would be a chiral molecule. A chiral molecule. Okay? Again, if you're struggling to view it or just imagine it, I should say, what would be a good idea to study with what? Starts with M, ends with autols. Anybody? Models. Okay, you get a model kit, and if you're like, I don't have one, you go up to the Science Center. They have, not Avogadro's number of them, but they have quite a few that you can borrow. Has anybody ever borrowed a model kit from the Science Center? Nobody? Yes? Okay, well, they have them, and you can definitely go up and build the models and see that they are non-superimposable. This last one is another one that's kind of interesting. So we're going to do the same approach. If I give you a chair, just draw it out as a flat structure or just a regular bond line structure. I'll ask you guys again. So this is 1,4-dibromocyclohexane. Is this a trans molecule or a cis molecule, you guys? Don't be shy. Holler it out. It is trans, right? One bromine is up. One bromine is down. This one is up and equatorial. This one's down and equatorial. Down. So this is certainly a trans compound. There we go. But this one's interesting, isn't it? Right? Because they're not 1,3 disubstituted. It's 1,4 disubstituted. So if I take a second and I draw the mirror image of this guy, and I'm not the best at doing this, but anyhow, there we go. So if I draw the mirror image, are those two molecules, and again, I would never try to trick you. It's not a trick question. I love it. Are they superimposable? Could you guys see if they are or not? I think so. I think they are. I think they're superimposable, right? You could do it. There's a couple of ways you could think about it, right, Eric? You could just take you could take this one, right, and you could just rotate it 180 degrees, and you could plop it on top of the other one. It would be a perfect fit, right? There's nothing wrong with that. So these two molecules are identical to each other. Does that make sense? Okay, so since these two molecules are identical, so we'll scribble down here that these are identical. Therefore, this must be achiral. All right, there you go. Okay, so a little bit about chirality. Go ahead. I'll start with Eric.
Just could you have also gone there by just saying neither of those were chiral centers because they're kind of attached to the same group as well?
Exactly. Yeah, totally. Go ahead. Same thing, right? So what these guys are saying, if you're not following them, is they're saying, well, hold on, Mr. Dion. This carbon and this carbon, I knew before you even started. Neither of those are chiral centers, right? They're attached to 4 groups, but there's 2 of them that are identical, aren't they? Now, hold on. If you're not following, watch. We'll just do the one in green, okay? Just the one in green because they're the same, okay? But the one in green, that carbon is attached to a hydrogen. It's attached to a bromine. But on this side, it's attached to a CH2, and this side, it's attached to a CH2. But remember, we're organic chemists. We don't stop like that. We keep digging. We keep going, don't we? Then we say, well, let's keep going and see if we can find a point of difference. We go to the next carbon. Oh, it's still another CH2. Then they meet at the same place, which is identical for both of them. So they have the same pathway going on those yellow highlighted carbons. And so neither of those are chiral centers, are they? Right? Absolutely. So I would say you guys, bravo. Okay? Absolutely, you're 100% correct. And either way works. You can draw the mirror image, see if it's superimposable, but these guys were sharp enough. They said those weren't even chiral centers to begin with. Absolutely. You're 100% correct. I love it. All right. Let's move on to section 5.3, which is arguably one of the more important sections of this chapter, which deals with what's called the Kohn-Ingold pre-log rules. Like I told you before I started the lecture this morning, I said my students usually forget those three names, but they sure remember R and S, okay? They remember R and S, and so if we're in organic chemistry too, let's say you guys take it with me in August, and then it's like September, and I say, do you guys remember the Kohn-Ingold pre-log rules? And you're like, what? R and S? Yeah, of course, I remember that, okay? So R and S is the Kohn-Ingold pre-log rules. Now, if we take a look at these two compounds that are shown on here, we see that these are enantiomers, right? They're mirror images, and you're like, hold on, they're not mirror images. Like, why didn't they draw a reflection? Well, instead of drawing a reflection can be pretty cumbersome. If we go back to that vitamin C, right, that we drew we looked at a few minutes ago, can you imagine trying to draw the mirror image of that? Not fun. Okay, and again, I don't like to let the E word come out of my mouth a whole lot in organic chemistry. It doesn't really belong here, but I will use it. The easiest way, so listen to me very carefully, the easiest way to draw the enantiomer of a compound, and we're going to try it in a little bit, is take every dash and change it to a wedge, and every wedge and change it to a dash. So you see that in this molecule, there's only one chiral carbon. It's this one that I have highlighted in blue. So to draw its enantiomer, if you're like, that's all I have to do? This is a wedge, I just change it to a dash, and da-da-ding, like that's it? I get the enantiomer? Yeah, that's it. You don't have to draw mirror images. You don't have to practice drawing the reflection and stuff. You just change wedges to dashes, and you get the enantiomers. So we say that these have an opposite configuration at the chiral center, okay? And we use Kohn-Ingold pre-log rules to designate these chiral centers as being what we call R. R is for rectus, okay? R is for rectus, which is to the right. Okay, so this is German. And S is to the left. What's left in German? Anybody? Sinister, right? So if you're left-handed, right, it's sinister, okay? So yeah, like, really? I'm sinister? I am, okay, I'm left-handed. So there you go. So rectus to the right, and right to the left is sinister. Anyhow, so we use R and S. So the way we would differentiate these compounds is designating one as an R compound and the other one as an S compound. And I'm going to teach you how to determine whether the carbon is R or S. Do you guys remember the periodic table? There's two on the walls in here, okay? What governs the identity of an element? Anybody know the number of what? Protons, right? It's the number of protons that governs the identity of an element. Hydrogen has an atomic number of 1, which means 1 proton. Helium has 2, right? Lithium has 3, beryllium has 4, so on and so forth. And so what we're going to do is, first of all, we're always going to differentiate atoms by atomic number, and the higher the atomic number, the higher the priority, okay? So the king of the castle is always going to be the element that has the highest atomic number. So if we just examine this carbon that I have highlighted in blue, that's not a very pretty letter C. Maybe I could spice it up there. There we go. That's a little bit better. Okay. So you can see that this carbon is attached to a hydrogen, which is not drawn, but it's implied that it's there. Which of the atoms that carbon is attached to has the highest priority? Is it the oxygen, the chlorine, the hydrogen, or is it this carbon, which isn't drawn? I'll just pencil it in. It's chlorine, right? Chlorine has an atomic number of 17. So chlorine is the king of the castle. You know what we're going to do? We're going to call chlorine number 1. Okay, so I'm going to put a number 1 by it, all right? So we'll put number 1 here. Which one is the loser? Which one is just the lowest priority? Can't go any lower than that. You can't go any deeper. Hydrogen, you're like, stop talking, I was saying it. Okay, good. All right, and then we have a battle between oxygen and carbon. Who's a higher priority, oxygen or carbon? Oxygen, right? Oxygen is a bigger atom. I shouldn't say bigger. It's got more protons in the nucleus, right? It's actually smaller in diameter. But anyhow, so now what we do is this. Are you ready? I'm giving you the Sparks Notes version of the rules because I know you guys are all super astute. I know one thing I've learned teaching organic chemistry is that my students are usually very fast learners. And if you think you aren't, you are. Okay, trust me, you are. You guys are all fast learners. So I'll give you the 30-second version of the rules, then we'll go over the whole gaudy thing, okay? The rules go like this. You take a stereocenter, and the best way to view a stereocenter is to put the lowest priority group going away from you. So you see the lowest priority group, which is the hydrogen. If you can get it on a dash, that's the holy grail, okay? It's in the back. You can forget about it. So put the lowest priority group in the back. Then what you do is follow, like, you know that song, All Around the Mulberry Bush, right? But here we go all around the chiral carbon, okay? So we go around the chiral carbon from 1 to 2. See, we do a little walk. We're going to go from 1 to 2 to 3. Everybody knows how to count? Good. So here we go. We're going to go from 1 to 2 to 3. Now, which way are we going? Are we going to the right or are we going to the left? We're going to the right. Are you with me on that? We're going clockwise, so we're going to right. I see Heidi going like this. I do this all the time, right, Heidi? If I'm going like this, I'm going to the right-hand side. And therefore, we say that this stereocenter is R. Does that make sense to everybody? There you go. Don't worry, I'll go over the whole thing. So I always write a little squiggle line next to the chiral center, and then I'll just put the letter in parentheses like that. Now, hold on one second. I just want to show you one more thing. If you assign that one correctly, then this stereocenter must be what? It must be S, because it's going to be the opposite, right? R and S are opposites of each other. Go ahead. Then you throw down your books, run out of the room, start screaming in the parking lot, like, I can't do this No, I'm kidding. I'll show you. So what you're going to do, I'll go over in just a second. Just give me a second, and I'll get there. All right. There you go. So that's the Sparks Notes version. This is the more sanitized version of it. So here's what we do. I'm just going to review it. R or S is assigned. So we use atomic numbers to prioritize the 4 groups that are attached to the chiral center. 1, 2, 3, 4. Arrange it so the lowest priority group, right? Whatever group number 4 is. So we'll say here number 4 faces away from you. So that means it would be on a dash. Count 1, 2, 3. If you're going clockwise, it's R because you're going to the right. If it's counterclockwise, it's S, okay? Now, handheld models can be very helpful, but you are not allowed to bring handheld models into the quiz, okay? You need to know how to do this by looking at it on paper, which you are all more than capable of doing. And so if we take a look at this example here, I can't remember if this is I guess this is the same molecule that we had before, right? The chlorine is 1, the oxygen is 2, the carbon is 3, and so we go 1, 2, 3. And so this stereocenter is R because we're going clockwise. You with me on that? Okay? Now, counting the groups, okay, 1, 2, 3, determine whether the order progresses clockwise or counterclockwise. So R rectus, so the steering wheel is going to the right. Left-handed turn, counterclockwise. Cool? All right. Now, if the lowest priority group, so this is going to address your question. If the lowest priority group is facing towards you, if you look at YouTube or other chemistry textbooks or talk to other people, you're going to get different answers sometimes. Well, I've taught this class a long time. I'm not saying that I know everything because I certainly don't. But what I think is the least complicated way to do it is this. If the lowest priority group is facing towards you, right, that means it's backwards. So you just read it 1, 2, 3. If it's R, you would switch it to S. And if it's S, you would switch it to R. That's it. So here's how I would do it, you guys. I'd say, look, the lowest priority group, the hydrogen, is coming towards me. That's the opposite of where I want it, right? So I'd say 1, 2, 3, okay? So I'd say this is going to clockwise, so I'd say it's R. You with me on that? So what I do sometimes is when I was a student, I'd do this. I'd write R, and then I'd say, no, it's not. I'd say it's reversed. This is actually S. Cool? Okay, so I do that a lot of times since I'm a teacher. Okay, I'll write down what you're seeing is R, but you know it must be the opposite, right? It's the exact opposite of it, okay? The old version of the textbook, actually, he had different ways of doing it, which are fine, but I feel like the most straightforward way is, again, if it's coming towards you, just read it as you see it and just change it. Just switch it. That's all you have to do. All right. Now, if you're like, okay, what about carbon-based groups, Mr. Dion? What do I do then? If you look at this chiral carbon here, okay, this carbon here, it's attached to a hydrogen and a hydroxyl. Now I think everybody can see that this group and this group are obviously different from each other, but they're both attached by carbon, so it's like, okay, well, where do I go? Like, which one's higher priority? It's a great question, and what you do is you make a list of the atoms to which the carbon is attached. So you start with a carbon, and then you go away from the chiral center, and you list what else it's attached to. So the carbon on the left is attached to, it's a carbon, right? That's this one, and then it's attached to 2 hydrogens. Same thing with this guy. We have a carbon, and it's attached to 2 hydrogens. And you're saying, well, those are just 2 methylenes. There's no difference between 2 methylenes, right? But then, if we go to this carbon, and we make a laundry list of the 3 elements it's attached to, the 3 atoms, okay, going away from the chiral center. Are you with me? It's attached to a carbon, yes? And it's also attached to a hydrogen that's not shown. You with me on that? Okay, so then we go to this guy here. Can you guys see a green pen if I use that? Can you see that? Okay, what's this one attached to? It's attached to this carbon, right? So we would make a list for this guy. We'd say it's attached to a carbon, but it's also attached to these 2 hydrogens. So we're listing them in order of atomic number. We're putting the highest atomic number. So which one of these groups is highest priority? It must be this one, because a carbon is going to beat a hydrogen. You with me on that? So now when we prioritize our groups, okay, this is the same molecule here. The hydroxyl has to be number 1 because oxygen has a higher atomic number than carbon. This has to be the loser, okay, it's number 4 because nothing can be lower than hydrogen. But we just figured out that this group must be number 2, and all of this group here must be number 3 because of that tiebreaker where the carbon is going to outrank a hydrogen atom. And so let's try it. I'll zoom in here. So we're going to go, I'll give you guys a second. Can you guys study this and tell me whether it's R or S, and I'll do it too. I could have put a circle around this. Is it R? Everybody else get R? Yes? Okay, how did you do that? You don't have to yell it out. I know how you did it. You went from 1 to 2 to 3, right, which is going counterclockwise, which would be S, but it's not S, is it? Because the lowest priority group is what? Coming out towards you. So you switch it. So I'm going to put here, maybe I'll put my squiggle next to the chiral center. So you'll say S. No, it's not. It's actually R. Okay? So when I cross out a chiral center, that's just me telling you as your instructor that the lowest priority group is coming out towards you. Cool beans? All right? And I'll stop doing it after a while. But since we're learning the subject, I like to do it that way. There you go, my friends. Now if you're like, okay, cool enough. I see this guy here. This group with the hydroxyl on it is going to outrank this tert-butyl group because this carbon is attached to an oxygen, then it's attached to these 2 hydrogens, all right? Whereas this carbon is attached to carbon. Okay, so it's attached to all 3 of these guys here. So you can see an oxygen beats out a carbon, right? So I'll give you guys a second to assign the chirality to this one too, and I won't number it. Go ahead.
Just out of curiosity, do you find it, like, for further applications, like, beneficial, like, probably the safe way for a quiz is to do the system we're doing in class, but do you find it beneficial to try to, like, visualize, like, looking at it from the back and then picture it?
I don't know. I don't. Maybe some people do, but I certainly don't. You could if you wanted to. Yeah, so if you visualized it from the back, you'd be going like, yeah, you'd be going like this, which would give you what? What's the chirality? Anybody? R, yeah. So Eric, I have to, there's only so many things I can teach. So yes, you could certainly view it from the back, but some people find it easy, some people find it very challenging.
It's more like, is that a skill that, like, working on that?
Oh, sure, yeah. People pick it up after a while. You get used to looking at them, but most people have to think about it for a second, you know? So all Eric is saying is, imagine you were standing behind the screen and looking at it. Well, then the hydrogen would be in the behind you, right? So you can envision it that way. But again, I'll just do it the way we were doing. So we'd say 1, we'd say 4, we'd say 2, we'd say 3. So we're going 1, 2, 3, which is S, but it's not S because the hydrogen is coming out towards us. And so it's R, like that. I'll show you an example where I do like to look at it from a perspective in just a second. You brought up a good point, okay? So let me show you. Let's take a look at this one here. Now, if you're sitting there going, Yeah, but what about double bonds? And what about triple bonds? What do I do then? Okay, the way you do it like this is double bonds count like 2 single bonds, and a triple bond counts like 3 single bonds, okay? So when you're making your laundry list, that's all you have to do. So if we go by this carbon here, obviously this oxygen is 1, this is 4, but if we look at this carbon here, it's attached to a carbon and 2 hydrogens, so CHH. But remember, each of the double bond, or each of the bonds in the double bond to oxygen, they each count as 1. So it's like oxygen, oxygen, and then the hydrogen on that aldehyde group, okay? And obviously, oxygen beats out carbon, and so the aldehyde group is going to be higher priority than the propyl group that's over there. Does that make sense? Okay, let's do it again. Let's keep practicing. I'll give you guys a second. I'll erase some of the spinach that I put on here. Maybe that'll help. So could you guys tell me what's the chirality of this guy? It would be S. Yeah. So I have 1, then I have 2, then I have 3. This one's nice because the hydrogen is behind us. So we go from 1 to 2 to 3. It's going counterclockwise, and so it's S. Got it? Or even if you're like, yeah, I think I have most of it, by the time you practice it, 50 times, you'll be like, yeah, I got it down, right? But who's with me on the rules? The rules are logical. I like to think the rules are logical. All righty. Now this is, students will ask me this all the time. Do you have a summary of this? Okay, well, here's a summary, okay? A review of the Condon-Gold pre-log rules, which again is just a Tsatsi word for R and S. You identify the 4 atoms directly attached to the chiral center, prioritize them based off of what? Atomic number first. If 2 atoms have the same atomic number, like 2 carbons would be what we run into the most, then you have to make that laundry list. Remember, you're going away from the chiral center, and you look for a tiebreaker, or the first point of difference. If you have a double bond, it counts as 2 single bonds. If you have a triple bond, it counts as 3 single bonds. There's one thing that's not mentioned in here, and if it is, forgive me, because I haven't noticed it, and I do read the textbook quite a bit. But if you want a shortcut, if you're dealing with R groups that are just straight chains, methyl, ethyl, propyl, butyl, pentyl, hexyl, heptyl, those kind of things, not branched. So don't say, what about isopropyl? No, that doesn't work the same way. But if your branches are just linear chains, the longer the chain, the higher the priority, always. Okay, if it's a methyl versus an ethyl, ethyl wins, right? If it's a propyl versus a butyl, the butyl wins. Okay, longer chain, only for straight chains though. Once you get into branch chains, you can't use that rule. Okay, so you guys recognize this compound? Maybe not. This is L-dopa. Okay, so this is L-dopa. L-dopa, and what's unique about why can't we just give dopamine, to people? Straight dopamine. Do you guys know what happens if you have too much dopamine? What's that? Yeah, and then what do people develop when they get too much dopamine? What's that? Yeah, I'd say it's usually schizophrenia. Schizophrenia is what they get. Yeah, there was a guy in my hometown. I'm going to have to edit this, so don't record this, anybody. But there was a guy in my hometown that had too much dopamine, and he ended up with serious problems. And, I remember me and my brother saying, we said, he's funny. And I remember my mom saying, there's nothing funny about that, this is very serious. It's a very serious condition, Anyhow, does anybody know what happens if you have a deficiency of dopamine? Do you know what happens? What do you get then? It's what causes Parkinson's disease, yeah? So Parkinson's, where they have monotonous speech and tremors and everything, Anyhow, I'm related to somebody that has Parkinson's disease, anyhow. Maybe somebody here is related to somebody with that. But anyhow, so L-dopa is an interesting compound because it can cross the blood-brain barrier and it can be metabolized to dopamine to help those people. There was an interesting documentary made years ago on public TV where they're giving these people huge amounts of L-dopa and alleviating their Parkinson's symptoms. Pretty fascinating stuff. Anyhow, that's enough about that. Do you guys, so this would be an amino acid, right? Because it has an amino group in it and a carboxylic acid in it. Anyhow, while I was talking, did anybody, Catherine, did you figure out whether it's R or S? While I was yammering on, there's a hydrogen that's left out. But there's only one chiral carbon in here. Did you figure out whether it's R or S while I was talking, or did anybody? There's 2 chiral carbons. I think there's only one. And this one would be the only one, right? Because this is a CH2 group, so that can't be chiral, right? So I'll give you guys a second to study it, and I'll study it too, because I didn't write anything down myself. So what would it be? R or S? Anybody? S? Is that what you got? Anybody else get S? Yeah, I think you guys are right. Let's scribble it down. The nitrogen certainly takes highest priority. This carbon here, you get a double bond to oxygen and a single bond to oxygen. O, 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 you know, all right? And then we have this, where's my other, this carbon is attached to, or this carbon is attached to a carbon here, but then it's also attached to these two hydrogens. Well, the tiebreaker here is certainly oxygen, which is a higher atomic number than carbon. And so we assign this group, where's my red pen? 1, 4, 2, and 3. So we're going 1, 2, 3 like that, which is R, but the lowest priority group is coming out towards us. And so the chirality is S. Okay, good. Mr. Dion can't hear that well. Thank you, you guys. Okay, an S compound. All right. Now, do it a million times. No. Okay, so what I'd like you guys to do before class on Friday is I want you to tackle these. I feel like I spent quite a bit of time on the rules, okay? So you guys can assign. And I've doubled these, so you see I put ephedrine, then I put ephedrine again. So the reason I put it twice is so I can scribble on the slide. We can do this chiral center, and then we can do this chiral center. The same thing with this halogenated compound down here. We can do this chiral center, and then we can do this chiral center. And I just did it so I could leave my scribbles up on the screen for everybody. But we'll tackle this on, what did I say? Friday. All right, so everybody give these a try, okay? Don't be shy. Don't be afraid. Go for it. Give it the old college try. Go ahead.
So our, having the 3 moles, whatever.
Yeah.
That, the system sounds perfectly logical, but did we just pick like the atomic number just because we needed a way to classify it? And people said this
Yeah, I guess so. I guess that's how they did it. Yeah, they just came up with a set of rules. Yeah. Yeah, there you go. All right, so now if you're wondering, well, how do I put this in a name? Maybe you weren't wondering it, but I'll tell you anyway, okay? So if you had these two compounds, right, if I asked you guys a question that you guys would just giggle at me, you know, if I asked you something like, what's the name of this compound that I've drawn in blue? You're like, oh, Mr. Dion, stop wasting my time. 1, 2, 3, 4, 5. You'd say it's 3-methylhexane, end of story, right? But you can see there's a chiral carbon in there, isn't it, okay? So now you guys are wise enough to say, that compound has a big, juicy chiral carbon in it that you kind of left out of there, Mr. Dion. Is it a wedge or a dash, you know? And then you see that somebody wrote out both of the enantiomers, the mirror images, right? Remember I said to make a mirror image, you just change the wedge to a dash. And so the way that we differentiate between them is with the nomenclature, is putting the chirality at the beginning of the name. So we start with the S here, right? Because you have the hydrogen in back. Right, this is a propyl group. It's going to take highest priority. This is an ethyl group. It takes second highest priority. The methyl group takes third highest priority, and then the hydrogen is going to be lowest priority. And so we're going 1, 2, 3, which is counterclockwise. And so yes, this is an S compound. Thus, its enantiomer must be R. So we just write the chirality, R or S, and we put it in parentheses. Now, if you're going, yeah, but what if there's more than one chiral center? Well, you have to put a locant or a number in front of the chiral center that you're designating. So here we have 2 chiral centers, so we have 2, 3, 4 trimethylheptane. However, in this compound we have this is carbon 3 and this is carbon 4 here, okay? And so we put the chirality, right? But we put a locant, a number designating that in front of it. Cool? All right. Why isn't this one a chiral center? This one. The one that I have the black carbon on. Anybody? Why? 2 methyl groups, right? See, you guys starting to pick up on it very quickly. You're like, I recognize that. You don't, I can do that faster than you can, okay? Great. That's awesome. That is awesome. Good. Now let's move on to Fischer, the Fischer projection, okay? So in Organic Chemistry 2, we will do a whole chapter on carbohydrates, okay? We'll do a whole week of just sugar chemistry. We'll get some more practice drawing our chairs, okay? We're going to draw lots of chair forms of different carbohydrates and stuff. Also, so when we deal with carbohydrates, we're going to look at a lot of Fischer projections. And the reason that Emil Fischer developed the Fischer projection is because he was a human being And just like all human beings, he was work smarter, not harder, right? And so he got tired of writing, zigzag formulas and all these dashes or wedges and dashes, and he got tired of it. And so he said, there's got to be an easier way. And so he developed the Fisher projection, which enabled him to distinguish different carbohydrates very quickly, okay, very rapidly. And so if you don't remember this, I went over it with you briefly, I think, on another class. But in a Fisher projection, like this one here, okay, the horizontal lines are coming out of the page as if they're coming to give you a big hug. I should have taken a picture off of Google Images of somebody going like this, okay? But anyhow, so these are going to be horizontal and they're coming out of the page. You can see that's what's going on here. Then the vertical lines, as you can see, are going back into the page, okay? So going back into the page. Now, if we look at this carbon here, you guys, all of us can tell that this is a chiral carbon, right? It's attached to 4 different groups. Now, is this carbon R or S? What we're going to do is this. Let me show you. I'll show you how to do it very relatively quickly. So we have 1. Obviously, the hydrogen is number 4. Which one's higher priority, ethyl or methyl? Ethyl, because it's longer, right? So 1, 2, 3. So what we're going to do is we're going to go around the chiral carbon and we're going to go 1, 2, 3. So we are going clockwise, which would be R. But the lowest priority group, which is the hydrogen, is it on a dash? It's on a wedge. So instead of being R, we say it's S. Same old trick as before. Thus, and I'll repeat myself, if your lowest priority group is horizontal, you have to reverse it, right? Because it's coming out towards you, right? You have to flip it. Okay, Fisher projections. What are they useful for? And this is kind of backtracking here. They're most useful when you're drawing compounds that have multiple chiral centers. For example, carbohydrates. So you see we have 2 chiral centers. Then here we have 1, 2, 3 chiral centers. Here we have 4 chiral centers. All right. So yeah, anyhow, there you go. So that would be a form of glucose there. Now, when it comes to Fisher projections, this is kind of new, this slide here. This wasn't presented the exact same way in our old textbook. This is new for the 5th edition. So this is the first time I've ever used this slide in class, but I used my own version of it before. I think the reason why he put this in here is, he gets feedback from other people, and there's a co-author now on the textbook, is that there's quite a few questions, I think, now in those MCAT prep materials and on the ACS study guide and things where they ask a lot of questions about Fisher projections. And it's because, the MCAT has leaned more in biochem flavor now than organic chemistry. But you have to master organic chemistry before you can even get to biochem, right? And so just what is allowed with the Fisher projection? That's kind of like what the title of this slide should be. I didn't put a title on it, but the title could be Things I'm Allowed to Do with the Fisher Projection and Things I'm Not Allowed to Do with the Fisher Projection. And so things you're allowed to do, you can see there's a lot more not allowed than allowed, isn't there? Something that you can do with the Fisher projection is rotate it 180 degrees. Why? Because the dashes are still dashes and the wedges are still wedges. You see, everything that was on a wedge is still on a wedge. Everything that's on a dash is on a dash. And sometimes, not you guys, but sometimes students will be like, I'll just rotate it 90 degrees. You can't do that. Why can't you rotate it 90 degrees? Because you see that when you rotate it 90 degrees, now what was a wedge is now a dash, right? And what was a dash becomes a wedge, okay? So it's going to mess it up. Go ahead.
What would be the benefit of rotating your Fisher projection 180 degrees?
It can help you in trying to designate chirality sometimes. Yeah, if your lowest priority group isn't in the right position, that's usually what we use it for. It's a great question, right? So also, a pancake flip is not going to be allowed, right? You can't just take it, scoop it up in your hand and flip it over, right? Because again, it's going to change it, right? You see your wedges become dashes and your dashes become wedges. So really, the only thing you're allowed to do is flip it head for tail. That's all you're allowed to do. You can't pancake flip it. You can't rotate it partially. Otherwise, it's going to mess it up. Now, Kai, to kind of weave in your point there, look, you guys, don't panic about it. Don't be like, oh, no, I'm only allowed to do certain things. This is going to be so difficult. No, it won't be, okay? It's totally reasonable, okay? And I think, Kai, let me give you more background on the question that you asked, is that normally when we're designating the chirality of a chiral center on a sugar, you notice that at the top you have these carbonyl groups. Well, what has a higher priority? Those carbons that have 2 bonds to oxygen, or these ones down here that only have 1 bond to oxygen? So normally we put the highest priority group at the top. It's just the standard way that we do it, okay? And it's not me, it's all chemists do it that way. Highest priority carbon will be at the top. Cool? So that's why you would do that. Now, we don't have time to do all these. It's getting late in the lecture here, but let's try the first one. Okay, we'll try the first one, and I'll give you guys a second to try this because the lowest priority group is not a hydrogen in this case, is it? Right? I'll give you a second to look at it. Excuse me. Anybody get a chirality for this guy? Don't be shy. I'll give you another second to look at it. Percy, did you get something? Is it S? Is that what you said? Yeah, I think it's S. Anybody else get S? Yeah, absolutely. Thank you. All right, our lowest priority group, the methyl group, is coming out towards us. I'm just going to draw on a wedge because I'm your instructor. You are not obliged to do this. It's just to prove a point. We go from 1, which is the chlorine, to 2, which is the carbon attached to 3 oxygens on that carboxylic acid, then down to the ethyl group. And so we're going R, but we know it's not R, is it? Right? Because the lowest priority group is coming out towards us, and thus it is S. All right? So if we have time, we'll tackle these ones on Friday morning as well. Okay? We can take a look at these ones, and I'm sure you guys can do it so fast it would make my head spin. All right. Now, something that you're asked to do every once in a while in this class is take a bond line structure like this one for ribose, and then you're asked to draw the Fisher projection of it, okay? And so now what we're going to cover is how do you draw a Fisher projection from a bond line structure? So how did he get from here to here? How did he do that? Because if you rotate this molecule so that it has an orientation like the Fisher projection, remember, all the vertical bonds are going back. So if you made a model of that, right, the way it is, it would curve backwards. Are you with me on that? It would look like this, right? If you were looking down from the top, if this is your eyeball here, it's curving backwards, okay? There's even an exercise in one of the organic chemistry textbooks where it says, make it on a piece of paper and then like tape it backwards and then study it or something like that. So what you're going to do is this, okay? Now I know it looks like there's a lot on here, but the way you're going to do it is this, is what you're going to do is you're going to say, okay, my most oxidized carbon is my highest priority carbon is the one with the carbonyl here, which is not a stereocenter. I'm going to put that in the top. Remember, CHO is the condensed formula for an aldehyde, and this is an aldehyde. Then I have my CH2OH down here. I have a total of 1, 2, 3 chiral centers. I'm not using nomenclature numbers. I'm just calling them stereocenter 1, 2, and 3. If you wanted to use nomenclature numbers, we would have to start here. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Now what you do is this, okay, is you take this structure, and for this first carbon here, so carbon 2, you're trying to figure out, is the hydroxyl going to be on this side or is it going to be on this side? What you do is you imagine yourself on top. Why on top? Because you see how these two bonds are pointing upwards towards that chiral center? If they're pointing up, you imagine yourself on top, like this. If they're pointing down, like on carbon 3, you imagine yourself below it, okay? So imagine yourself on top. I'll delete this guy here. So imagine you're right here. When you're looking down, what do you see? You see the hydroxyl is on your left-hand side. Everybody with me on that? Yes? And so you would fill it in. You'd say hydroxyl is on the left-hand side. Then for carbon number 3, you're going to imagine yourself underneath it. When you're looking down from the bottom, the hydroxyl that's on that dash is on which side of you? On your left-hand side again. So you fill it in, okay? Then we go to the last one, which is carbon number 4. You imagine yourself on top. Why? Because these two are pointing upwards. So you imagine yourself on top. You see the hydroxyl is on your right-hand side in this case. And so you would put it over here like this. Everything else is a hydrogen that's missing. There you go, my friends. That is how you do it. Is that cool or what? I love his person drawing there. It's like he's such an organic chemist. He thinks of people as just being a couple of bonds and a sphere on top. It's like the medical community. If you ever see those commercials where they just show a body like this with a mouth open and there's like lightning or something. This is the way they think of us. It's just a thing, a hole with some lightning in it. I'll cure the lightning, right? Feeling any lightning these days? No, I'm not feeling that. All right, so let's see if we can do a bond line drawing of, we'll just do the one on the left for now. So we have our most oxidized carbon, number 1 at the top. So we have CO2H. Carbons 2 and 3 are chiral centers. So we'll say carbon 2 is a chiral center, carbon 3 is a chiral center. Then we have our CH3 group down here. So I'll put the numbers the way he has them, 1, 2, 3, 4. So for carbon number 2, and forgive me because I'm not a very good artist, if you imagine yourself as being, what's that? Is that okay? What do you think of my person? That's pretty good. That's a very David Klein-y kind of person that I drew up there. So imagine yourself on top. So you guys, if you're on top of that, which way is the hydroxyl going? On your left or on your right? It is on your left. What am I spending time on this for? We should be talking about something else, okay? You guys are way ahead of me. Now, watch this. Yeah? See what I did there? All right, the guy just went down to the bottom. So now he's on the bottom. The hydroxyl is on his. There you go. Cheapers. Remember to tell you guys something at the end of class. So there you go. You're going to do the exact same thing for the next compound, right? You're going to say CHO, right? That's your aldehyde, the condensed form for an aldehyde. Then we have 2, 3, 4. So we have 3 chiral carbons. So put here 2, 3, 4. I realize that's not the prettiest writing ever. CH2OH. So this is 1, 2, 3, 4, 5. And I want you guys to try filling those out. All righty? Who remembers intermolecular forces? Anyhow, so intermolecular forces. Reason I bring that up is, have you guys ever been to IKEA before? It's this store. It's like this cruel joke played on us by the Swedish. Anyhow, they made this thing up just for us, just to be like, haha. Anyhow, it's a joke. Anyhow, but if you look at these two molecules here, so this is R carbone. I'll even put my pencil down here for a sec. So this is R carbone and S carbone. Obviously, they are enantiomers, right? Because you see the wedge in R carbone has been flipped to a dash, so there's only one chiral center in the compound. But if you imagine those as just objects, now obviously they are, they're molecules, which are objects in a way, I guess. But if you tried to stack a bunch of R carbone molecules as efficiently as you could, right? Stack them up like plates. Are you with me that the S carbone, you'd be able to stack them just as efficiently? Right? There's no differentiation between the way that they would stack. And so if you have a mole of R carbone molecules interacting with each other, they're going to interact with each other the exact same way their mirror image would. Are you with me on that? So that's why if you have enantiomers, you can't distinguish them by physical properties. Impossible. They have the exact same melting point. They have the same boiling point. They have the same density. They have the same refractive index. Their infrared spectrum is identical. Their mass spectrum is identical. Later on, we're going to look at NMR. The NMR is identical. You're like, well, crap, we're really out of luck here. How are we going to differentiate between these two? It's a great question, and it's one of the most crucial things that we have to answer here. But it turns out your body can identify these two enantiomers a lot cheaper than buying a spectrometer because they taste different, right? They interact with your receptors differently. The R tastes like spearmint. In fact, if you smell it, it smells like spearmint, whereas the other one tastes like caraway seeds, right? Which is used to make like, what kind of bread? What's the dark loaf there? Rye, yeah, in a rye bread, yes. Thank you, okay? Anyhow, yeah, are you with me on that? So again, listen to me very carefully. Enantiomers, you're out of luck, right? Your nose can differentiate, right? But can't use IR, can't use mass spec, can't use melting points, boiling points, flash points, refractive indices. You're out of the, so if you're like, I quit, like how am I going to tell the difference between two molecules that are odorless? It's a great question. And it brings me to sunglasses. All right? The future's so bright, I've got to wear shades. Right? Does anybody here have polarized sunglasses? Right? I had a friend who I had a pair of Coco Chanel sunglasses, and I was like, how much are those? She told me, I was like, you're joking. Anyhow, so, but you can buy polarized sunglasses. I know this because I've done it. You can buy them from Jeff Bezos. You can get a 3-pack for like $15, okay? They're amazing, you know? So anyhow, so polarized lenses. All right, so it has something to do with polarized light. If you've never seen polarized sunglasses, has anybody ever seen polarized sunglasses at the store and they have the little hang tag on them that you can put it in front and rotate it like that? Yeah, it's to prove that it's an actual polarized lens, like fake, you know? And then you're like, oh, these are the real deal, you know, because it cuts out the light. So you guys remember electromagnetic radiation from the last chapter? So it turns out that light, okay, oscillates, as you can see here, and enantiomers that have opposite configurations, obviously, R and S, can rotate plane polarized light in opposite directions. So you guys know that light has an electric field and a magnetic field, and they oscillate perpendicular to each other with the same frequency. But the take-home message is this, is that what you're going to learn in the next 2.5 hours with me, because today's an extended class, is that what happens is that when you subject a chiral compound to plane polarized light, it rotates the light. So if you have two enantiomers, the way you differentiate between them is that they both rotate plane polarized light to the same amount, but they rotate it in opposite directions, okay? So one's going to rotate it 23.1 degrees Celsius clockwise, and the other one's going to rotate it 23.1 degrees, not degrees Celsius, I'm teaching too much, degrees in the opposite direction. Are you with me on that? Now, before you get too excited, because I remember when I was a student, I was like, hot diggity damn, this is going to be awesome, because R is going to be positive, S is going to be, you know, I thought there's going to be some correlation. Sorry, there's no correlation whatsoever between whether it's positive or negative and R or S. The only way to know, put on a lab coat, safety glasses, go into the lab and measure it. Okay, there's no way to know. But the way we differentiate between enantiomers is the way they rotate what's called plane polarized light. So if you're like, what's plane polarized light, Mr. Dion? Well, if you just take white light from an incandescent light bulb, okay, what happens is that the light is coming out in waves that oscillate in all directions. But if you pass it through what's called a polarizing filter, and so if you have polarized sunglasses, it has a polarizing filter, so all directions of the light can't come through. It just allows one to come through that's in the same orientation as the filter in your glasses, okay? So instead of having light in all directions, when you pass it through a polarizing filter, it's only going to be coming out in one direction, like that, right? Just like Harry Styles. And so then what you're going to do is you're going to take the plane polarized light and you're going to shine it on a sample of an organic compound in solution, okay? So we have a polarimeter, and if you guys, I don't know if there's one in your lab. Which lab are you guys in? Are you guys ever in 256? In that room with Dr. Lakakula? I don't know which room you guys are in, but in one of those rooms, there's a polarimeter sitting in there, okay? So you could ask her, you know, just say, oh, where's the polarimeter? And she'll point it out to you. But a polarimeter has a tube here, and you make a solution of an organic molecule. It's usually in some kind of solvent, you know, of your choice, maybe dichloromethane or something like that. Then you have your light source here. We use the D line of sodium. So the D line of sodium, which is a wavelength of like 590 nanometers, something like that. You shine the light through the polarizing filter, and then what happens is that the molecule, okay, so this is the molecule, which is chiral, is going to rotate the light to a certain amount. So one enantiomer is going to rotate it a certain amount, and the other enantiomer is going to rotate it in the opposite amount, but in an equal amount, okay? So what you do is you adjust this lens down here, is you rotate it until you see the light come through, and then you just measure the angle of rotation is all you do. Don't worry, I'm not going to make you write an essay about it, but to put a cap on it, it says here, and these are the kind of conclusions for you and me, our enantiomers will rotate plane polarized light to equal degrees, but in opposite directions. So one will be clockwise, one will be counterclockwise. If it's clockwise to the right, we call it dextrorotatory. If it's counterclockwise, we call it levorotatory. The degree to which the light is rotated depends on the sample concentration and the path length of the light. Standard optical rotation measurements are taken with 1 gram of compound dissolved in 1 ml of solution with a path length of 1 decimeter or 10 centimeters. Temperature and wavelength can also affect rotation and must be reported with measurements taken. I am not going to ask you to answer any questions about measuring an optical rotation or calculating an optical rotation at different concentrations. Why? It's not part of ACS, okay? It's not part of anything that would be in a final exam you guys are going to see. What I expect you guys to know is kind of what's on here. If you have two enantiomers, they're going to rotate plane polarized light in equal amounts but in opposite directions. RNS, that refers to chirality using the Kahn and Gold pre-log rules, right, everybody? Okay. The positive and negative, that has to do with how it rotates the light. Positive for clockwise, negative for counterclockwise. There's no correlation, unfortunately for us, there's no correlation between RNS and positive or negative, okay? The only way to know whether something rotates plane polarized light in the positive or negative direction is to do an experiment, okay? Is to figure it out your own self by going into the lab and doing it. All right. So again, this is adding to what I said. Positive rotation is called dextrorotatory and negative is called levorotatory. Again, positive is clockwise, negative is counterclockwise. And so this compound that's shown down here, this is aspartic acid, has an optical rotation of levorotatory at 20 degrees Celsius, but it changes direction at 90 degrees Celsius. And so you see, it's also temperature dependent. And so when we report an optical rotation, you probably were like, what's all this stuff here, okay? So what this has to do with is this means the D line of sodium, and this is the temperature in degrees Celsius. So the alpha just stands for the optical rotation, and there you have it, okay? But again, I'm not going to ask you much about this other than enantiomers can be distinguished by optical rotation. Are you with me on that? Is that cool or what, though? You're like, who thought that up? I want to hang out with that person. That person seems pretty cool to me. And so what we're going to do a lot of on Friday is we're going to look at pairs of compounds, and we're going to try to determine whether we're dealing with a pair of enantiomers or a pair of diastereomers. And thus, I'm going to introduce a new term to you next class. Diastereomers, which is a type of stereoisomer that are not mirror images. Now hold on, we got lots of time. It's only 9:13. We have lots of time left, okay? We've already seen examples of diastereomers this morning, okay? Remember when I showed you the cis and trans on the ring and the cis and trans with the double bond? Well, those cis and trans on the double bond, think about it. They're stereoisomers, but they're not mirror images. Therefore, they would be diastereomers, okay? And don't worry, we're going to review this on Friday. I'm going to go over it with you, okay? I don't like to leave any stone unturned, but if you figured that out already, you're 100% correct. These two compounds, the cis-2-butene and the trans-2-butene, are they stereoisomers? Would you agree with me on that? But they're not enantiomers. They're certainly not mirror images of each other, are they? Therefore, they must be diastereomers. So hold on, we still have a minute left. If I could make a recommendation, okay, I recommend that you try reading the remainder of the chapter before